So when we apply this, we can get better and better approximations if we shorten these line segments up. If you imagine this linear approximation being here instead, and then this one here, if we shorten the line segments or change the delta x by making it smaller, we can make these make the approximations even better. Okay, so this is our method of approximating a curve. Okay, by using these short straight line segments. So let's use Euler's method. We're going to calculate the general solution to this equation. Okay, so some of these we can anti-differentiate. So we can actually find the exact value of this by anti-differentiating this, because we can separate and integrate this. And we're also going to do this with Euler's method and compare the two. Okay, so we're going to use a table. Our table is going to use delta x of 0.1. And we're going to do it from x equals 0 to x equals 1. And we're just going to compare the values. So first thing is we're just going to anti-differentiate this. So we have dy by dx is equal to, it was y plus 1. Okay, so we separate and we integrate. So we end up with log 1 plus y is equal to, that would just be x, a plus c, we get y plus 1 equals e to the x plus c. We know that that c is going to be a k value, so k e to the x. We'll plug in to solve for k, so we know that x is 0, y is 1, so 1 k e to the 0, so k is equal to 1. So here's the solution to my differential equation. Y equals, sorry, I need a plus 1 here, don't I? Or sorry, minus 1. So minus 1, minus 1. So k is equal to, looks like k is equal to 2. Okay, so if k is equal to 2, then my differential equation solution is 2e to the x minus 1. So there's a solution to my differential equation. Okay, so there's our general solution. That's the exact solution. We're going to apply Euler's method now and compare that to that. Okay, so I'm going to do the first one for you. So our derivative is going to be 1 plus y. Okay, the y value is 1, so our derivative is going to be 2. So that's going to be the slope. The x coordinate was 0, the y coordinate was 1. Okay, so the first one's not an approximation. We know that's going to be 1, and there's going to be 0. Error is going to be 0. Okay, so when I plug in the next one, okay, so I know that my x coordinate, when I do my linear approximation now, I need to work out my derivative. Okay, so the derivative is going to be, or so my linear approximation equation is going to look like this. So this is the first one. Y equals, okay, y naught is 1, plus the slope is 2, okay, and x minus 0. There's my linear approximation formula. So my next x is going to be at 0.1. And maybe I'll do this at a different color. This is going to be at 0.1. So I'm going to plug 0.1 into this equation. Y equals 1 plus 2 times 0.1. Okay, so my first y approximation is going to be 1.2. Okay, so 1.2. Okay, and if I were to plug in my exact, well, we'll do a calculator to do that, but we can compare that to our exact value. Okay, so this is my first approximation. I want you to do these steps then to apply it for the next approximation. So for the next approximation, we're going to need to know the slope. Okay, so we're going to use the derivative to calculate slope. You're going to use that derivative and the coordinates to come up with another linear equation that is going to approximate the next point. Okay, so I'm going to get you guys to pause. I'm going to pause the video right now, and I want you to try this on your own. Then I want you to compare that to the results that I get.